Hey everybody, this is John. I wanted to do something different this week with the newsletter, so I put together this little video about passing gas. It's not what you might think it is, but I hope it did get your attention. A lot of media attention is placed on carbon dioxide and methane gas emissions today. The campaign to control carbon dioxide emissions as a dangerous greenhouse gas has been active since, well, Al Gore made it. The inconvenient truth is that the control of these gases is viewed by many climatologists as alarmist and expensive to fragile worldwide economies. But how come nobody's asking this question? How come nobody talks about where all the oxygen came from? That's right, the stuff that we breathe. How come no one's talking about the very slow destruction of the source of our oxygen? In order to understand this, we have to really take a look at the composition of our atmosphere today. And today, 78% of it is nitrogen, 21% of it is oxygen, and the remaining 1% consists of things like argon, carbon dioxide, neon, helium, methane, krypton, and hydrogen. Now, I don't know about you, but I can't relate to percentages. I need to put percentages in perspective. So if we were to take 1 million molecules of the Earth's atmosphere, here's what the percentages really mean. But the question still remains, where did all the oxygen come from? And interestingly enough, just as a side, notice the levels of carbon dioxide and methane. They represent a very, very small amount of the total atmosphere. So you might be wondering then, what is all this fuss about? Welcome to the confusion. In order to understand where the oxygen came from, we really have to go way back in time. The time when the planet was still hot and lots of the planet-forming geologic processes were still going on. A time of very active geology. A time when our atmosphere was forming. About 3.5 billion years ago, the Earth's atmosphere contained no oxygen. The Earth's atmosphere at that point in time consisted primarily of things like hydrogen cyanide, hydrogen sulfide, methane, carbon monoxide, nitrogen, carbon dioxide, and some water vapor. Most of these gases are deadly. We know that today. Whatever life was here was doing okay. Life was in the oceans. It was not on land. And as this life began to evolve, it needed to find different ways of producing energy. Some of these very primitive organisms had the ability to capture sunlight and convert sunlight into a form of energy that it could be used. These very primitive life forms we now know as algae. So in this ocean that is red because of all the iron in it, we begin to see algae evolve. And in this process of converting sunlight into energy, it gives off a very toxic gas, oxygen. And we begin to see the first mass extinctions. The highly reactive oxygen that is dissolved in the oceans now combines with all the iron and forms iron oxide. The iron oxide sinks because it's heavy, and later on, all this iron oxide is dug out of the oceans in the form of iron ore. And the oceans go from red to the blue-green that we know today. But the organisms that are still surviving have a problem. Oxygen is very poisonous. Oxygen is very reactive. These organisms can't adapt to the presence of this gas. They begin to die. They become extinct. But not all of them. Some of these organisms still exist today in the deepest parts of the oceans. As we study the volcanic vents on the bottom of the oceans, we know that the surrounding environment resembles the Earth's early atmosphere very closely, and we find an abundance of life that exists without oxygen, without light. So we know that the early Earth's atmosphere was very conducive to these conditions. Some organisms resist extinction by using the oxygen. These newly evolved aerobic organisms find a way to make oxygen part of their energy producing cycles. And this wasn't necessarily so much to produce more energy as it was a method of tying up this very poisonous gas. Fortunately, over the next couple of 100 million years, these aerobic organisms evolve to require oxygen in order to survive. In the process that we call cellular respiration today, we know that it produces, on a cellular level, a great deal of energy. And it's because of this poisonous gas that these very early forms of life had to tie up in order to keep from becoming extinct. As the oxygen levels in the atmosphere begin to increase, all the other gas levels begin to decrease. Life is still not on land, though. Life cannot survive on land because of the high concentration of ultraviolet radiation. With the increased levels of oxygen in the atmosphere, though, very high up, something very wonderful begins to happen. These oxygen molecules begin to combine, and they form a substance that we know as ozone. Ozone provides a blanket, a very good protective blanket against ultraviolet radiation. The ozone layer provides enough protection for life to come out of the oceans and begin to evolve on land. So we've come pretty much full circle. Do we really need to be concerned about carbon dioxide levels? Do humans really have an impact on carbon dioxide levels? And is it as alarming as we have been led to believe? And what exactly is this carbon footprint that we hear so much about? Well, climate's going to change no matter what we do. It's part of the process. Most climatologists today will say that the rising carbon dioxide levels may not necessarily be due to human activity. In fact, we know plants need carbon dioxide to carry out photosynthesis. So this is kind of like catch-22. If we decrease the level of carbon dioxide gas in the atmosphere, what happens to all the plants? And if they begin to die off, what happens to the oxygen? So it's a very complicated process. I think what we need to be more concerned about is the cutting down of the trees, the destruction of the rainforest, the very things that we need to produce more oxygen. Finally, there is this little bit of information the media seems to either ignore or have completely missed. Most of the carbon dioxide produced in the atmosphere today comes from the same place oxygen originally came from, the oceans. Now, the reason for that is very simple. The oceans act as a sponge. The oceans can absorb a great deal of carbon dioxide. In fact, the oceans contain about 50 times more carbon dioxide in it than the atmosphere does. And through processes like wave action, storms, this carbon dioxide is released into the atmosphere. Does this mean we need to drain the oceans now in order to control carbon dioxide levels? We know, for example, much more carbon is going to flow through the oceans than the amount produced by fossil fuels. So the question now becomes, what happens if the oceans can no longer absorb all the carbon dioxide? Well, that's another story for another time.